Okay, I just want to really briefly introduce some of the vocabulary we're going to use talking about light, and we'll be using this the rest of the term. So, yeah, we might as well do it. Um, Light is a traveling wave, is how we're going to deal with it, and you can think of it as something like a water wave or a sound wave. You know, water wave is just a changing water height. There were this maybe that would be like no wave, right? So here we go. The water height just sort of bounces up and down. Or you can think about a sound wave. Those are actually a little different because sound waves are called compression waves. So the waves are so the air is jiggling like this instead of rising up and down like water. But anyway, it's the same idea. And so this disturbance travels in some direction. Maybe it's the wave of people in a crowd in a football stadium, right? You stand up and you sit down, and you stand up and sit down. And the idea is that the wave speed moves at some speed v for velocity. The same thing is true in a big stadium, right? The wave kind of circles around at some speed, but the people aren't doing the moving. The people just get up and sit down, but the wave itself has some kind of speed as it goes around. And by the same token, in like a water wave, the individual little molecules of water, they don't move very much sideways. They just kind of bounce up and down. But the wave itself kind of moves over the surface. Guitar string, violin string, same idea, right? The string bounces up and down, but a little individual piece of string doesn't move with the wave along the string. It just bounces up and down. Okay, so the amount that it goes up and down, we're not going to use this very much, but I might as well write it down. This is called the amplitude. For sound, this would be like the volume of the sound is how strong the vibration is up and down. That's called the amplitude. What we will use is something called, let's see, actually, just to make it a little bit clearer, let me write from here to here. The distance between one wave and another wave is called, that's a lower Greek letter lambda. This is lambda, if you've never seen it before. It's just sort of the custom to use that for wavelength. This thing is a wavelength. Lambda is the wavelength. Just the distance in meters, peak to peak, from one peak to another. How far apart the waves are, right? That's just the wavelength. Something else we can get is called the frequency. And usually we just use little f. And the frequency is in waves per second, or sometimes cycles per second. Oh, which is also called, you may have heard of this, or you've seen it, or hertz. It's just a shorthand. Something that vibrates at 2 hertz means that there are 2 cycles every second, 2 waves every second. So those are the 2 main characteristics of a wave that we're going to talk about, the wavelength and the frequency. It turns out you can get something interesting if you multiply those together. If you multiply lambda times f, what you end up with is the speed of the wave. I guess that kind of makes sense. If the waves are like 2 meters apart and you're getting 2 waves every second, then the wave is moving at 2 times 2 or 4 meters per second. I guess that kind of makes sense. But anyway, if you multiply these 2 things together, you get the speed of the waves. Now, here's the cool thing. For light, V is one number. All light, because all light is the same kind of thing, it's the same kind of vibration. All light travels at the same speed, and this is called the speed of light. That's not very inventive. Sometimes we use, Einstein started this I don't remember why. I don't know why he chose the letter C. But anyway, the lowercase letter c is just a shorthand for the speed of light. It's very special. And it's just a number. It's 3 times 10 to the 8th meters per second. 300 million meters per second. You can look that up in a lot of different units. It's also 186,000 miles per second. It's as fast as light goes. That's 7.5 times around the world per second. And that's the cosmic speed limit. We think nothing can go faster than that. So 300 million meters per second is c, the speed of light. All light travels at that speed. I keep saying all light, and you're like, what? There's just different kinds of light. Yes. We'll do that in just a second. Anyway, these are the basic relationships that we'll be working with. And really, more than anything else, we'll use wavelength. Okay, what makes one kind of light different than another? We can think about something that's a little bit more familiar, which is sound. What makes one sound different than another is just the pitch, which is the frequency of the sound, or the wavelength. Same thing. So for sound, you might have a vibration that might look like this, and another vibration that might look like this. Right? This one, the top one, has a longer wavelength, and since they go at the same speed, this would have a longer wavelength. Oops. And this would have a lower frequency, as opposed to this, right? This has a shorter wavelength and a higher frequency. Why? Because they travel at the same speed. So what happens is, when the top one comes past you, when the top wave comes past you, you'll notice a certain number of clicks per second. That's the frequency. But the bottom train of waves, as they go past, if it's going at the same speed, you just get more waves per second, right? Because they're crammed closer together. So if the wavelength is shorter, that must mean that the frequency is higher. So if the waves are more compressed, you get more of them running by every second. That's all there is to it. Okay, if that was sound, you would say that the top one has a lower pitch than the second one. The pitch is the frequency. For light, it's exactly the same kind of thing, except for light, the frequency or the wavelength tells you not the pitch like in sound, but it's the color. The color is given by, you can specify either one you want. Oops, either lambda or frequency. Either wavelength or frequency is fine. We are pretty much going to always use the wavelength. It just turns out that's a little more convenient. So how it works is, if you have, just think about if you have like a bobber on the surface of a water. So if you shake a little bobber up and down, you'll generate circular waves go out, right? We've all seen that. So if you shake the little bobber up and down, the waves go out. And if you have another bobber that's over some distance away, when the waves reach that bobber, it'll start to shake up and down because it's riding along the waves. You could even imagine sending some sort of message. You could shake you could shake the first one at a certain pattern, and then later on you could watch this one over here and it will shake in the same sort of pattern once the wave gets to it. That's how sound works. You probably already know that. You make sounds in your throat, they come out of your mouth, and then they shake the air. The air hits your eardrum, and your eardrum shakes in response, and that sends a signal to your brain, and then you have sound. For light, it's the same kind of thing. Something is shaking. What the thing is that's shaking, we'll talk about that next time. Anyway, there's something that's shaking, and it's causing a disturbance. It's causing a wave, right? It's a wave. It may be a little mysterious. A wave in what? Well, again, you're going to have to wait on that. Just imagine that there's some sort of a vibration in something. So the vibration moves along, and then the vibration enters your eye, and that vibration causes little cells in your eye to respond, just like the eardrum shakes. Little mechanisms in your eye, little cells in your eye respond, sending a signal to your brain, and you see stuff. Same idea. So something shakes over here, and that makes something over here shake in response. Okay, so how fast it's shaking tells you the color, which is represented as either frequency or wavelength. Our visible spectrum, visible light, runs from, let's see if I have these colors. I don't know if I have these colors or not. There's violet. Oh, good, that shows up. And then there is blue and green. And we're going to use them in this order. Yellow, orange, red. You know these colors. These are the colors of the rainbow, right? You always see these colors, and it's no coincidence that white light is broken up. White light from the sun is broken up into these colors, and these colors form what's called a spectrum, which is just a series of different colors, different wavelengths all running together. So these are the colors of the rainbow. You always see them in this order, and the way it works is our eyes are sensitive to violet light on one end, and that's 400 nanometers. A nanometer is a billionth of a meter, 10 to the minus 9 meters, really tiny. So 400 nanometers is almost like half a millionth of a meter. It's no surprise that's also roughly the size of the little receptors in your cells in your eyes that detect them. So it's no surprise that your cells in your eyes are about the same size as the light they're trying to detect. It's just a general principle. Okay, so if the light has a wavelength of 400 nanometers, we call that violet light. Red light, on the other end, is 700 nanometers. That's the human sensitivity range, sort of like the sensitivity to sound. There are some sounds that are very low we can hear, and sometimes very high we can hear. So for colors, it's the same deal. We can see all the way to violet, and then on one end, that's 400 nanometers, and then we can see all the way to red on the other end, which is 700 nanometers. That's it. Those are all the colors that we can see, and then you combine those colors together, you can get pretty much any other color you like. But you may be wondering, are there colors that we can't see? Yes. Just as there are sounds that you can't hear, there are colors that you can't see just because our eyes are only sensitive to certain colors. So what happens if we go, here's the visible range, which is V, B, G, Y, O, R, right? What if we go to the right? What if we are, what about colors that's too red for us to see? We call those infrared. Our eyes can't see it. It turns out our skin can feel infrared light as heat. So this is what you call heat, like on your skin. You can use your hands as a sort of an eye, right? If there's a fireplace in the room, you could imagine if you closed your eyes, you could pretty much tell where the fireplace was just by holding your hands out and then trying to move your hands in the direction. You can sort of feel where the heat's coming from. So you can use your hands as a kind of an eye that can see into the infrared. So we usually feel that as heat, but our eyes can't see it. You can go farther. Longer wavelength things are microwaves. Exactly the same things that you nuke food with when you put it in the microwave oven. All you're doing is just shining microwave light on it. It turns out the microwave light is just right to make water molecules jiggle, and when water molecules jiggle really fast, that heats things up. And then further, we call this the radio part of the spectrum. We have to be a little bit careful. Radio is a kind of light. All these are kinds of light, right? The only difference is just their color, just their wavelength. So radio is a kind of light. We also use that word for turning on the radio, which is a device that can listen to, oh, that's a terrible word. Hold on. Radio, the physical device, the radio, is something that's sensitive to radio waves, which are light. I don't know if I'm explaining that well. We use the word radio in two different senses, right? Radio is a kind of light. The box called a radio can see that kind of light, and it turns that into sound, right? So the problem is, here's the confusion. When people hear radio, they think radio, oh, that's a kind of sound. But it's not. Radio is a kind of light, and you can figure out how to make a box to turn it into sound. But in astronomy, when we say radio waves, we don't mean sound waves. We mean light, very long wavelength light. I'm sure that cleared it all up. What if we go light that's too violet for us to see? You've heard of it. It's called UV, ultraviolet. If we go further, we get X-rays. So if you break a bone, they'll shine X-rays, just a type of light, but it's a very energetic kind of a light. The energy goes up as you go this way. So that light is so energetic, it goes right through your skin and gets absorbed by the bones. And then further this way, oops, I'm running out of room. Further this way is called gamma. And that's everything on that side we call gamma rays. So as you go to the left, so shorter frequencies, let's say this. Also going this way, you have higher frequencies, shorter wavelength, right? Going that way. But this whole thing is called the electromagnetic spectrum. So the electromagnetic spectrum encompasses every color of light there possibly is. And we are only sensitive to just that tiny, tiny little range, red to violet, in there. So you might imagine that maybe there are things that happen in the universe in astronomy that we can't see, just as there are sounds we can't hear. So it turns out now we have telescopes, specialized telescopes that can see in all these different bands. Some of them don't penetrate the atmosphere very well, so we have to put them in orbit. The only things that can make it to the ground are visible light and radio. Everything else, infrared, microwaves, gamma telescopes, X-ray telescopes, UV telescopes, all those we have to put in orbit because the atmosphere filters those out. But we have telescopes that can see in all these different regions of the spectrum, which is very, very cool because we can see all sorts of phenomena that just don't happen to emit visible light. They emit light in these other regimes. Cool. So this is our basic vocabulary for talking about light. Wavelengths, frequencies, the visible range from 400 to 700 nanometers, and so on. So next time we'll start talking about how light behaves and then where it comes from.